Given that a curve has equation as given, find the coordinates of the stationary point. So it looks familiar in some ways, but we haven't done this, have we? Right. So yeah, I mean, let's have a quick think about whether we would be happy sketching the curve. I think it would be quite difficult, you know, but we know it's composed of familiar kinds of curve, which is fair enough.
What does it mean by stationary points? Like,
sorry?
What does it mean by stationary points?
Right, good point. Turning points.
Oh, okay.
Is that what you call them? You know what I mean by turning points? Sorry?
Yeah.
Have we recently called them turning points? We're just as likely to call them stationary points.
Okay.
And why would that be? Because if you had a distance time graph in particular, I mean, if you had a velocity time graph, nothing to do with it, because on a velocity time graph, a stationary point, where is the particle stationary? On a velocity time graph.
Constant speed. Where is it stationary?
Well, it's not a constant speed. So let's say
I thought you were saying when the gradient is 0, that's when it would be a constant speed. But
well, that's what I'm coming to. Yeah.
It would be when it's on the x-axis.
Yes, on a velocity time graph, it would be there. But you know, that's worth contrasting with the situation, isn't it? Where if this is a distance or displacement time graph, then that's what you meant, isn't it? Here is the stationary point, where the turning point, where it's a turning point.
Yeah.
That's where the particle is stationary, isn't it?
Yeah.
Yeah. So turning point equals stationary point. I mean, you might say, we're assuming that this was a displacement time graph then in that case. No, because we overgeneralize. We just refer to turning points as stationary points, whether it makes sense or not.
Right, okay.
Whether we're talking about something which is stationary or not. So it's just a sort of metaphor, really. Somehow or other in maths, these are considered to be where the curve is stationary.
Okay.
Yeah, right. So if it's about finding the coordinates of the turning point, I mean, if it's to do with periodic functions, cos and sine both look like that, don't they? Now, when you square cos, well, it would need to start there, wasn't it? It starts up there, doesn't it? If you square, of course, we might not start there. We might go in that half as well. But if you square this, you get something a lot like the mod of that. Because you're not going to get any higher, are you? Because the square of 1 is 1.
Yeah.
But minus 1 will become 1. And then the curve will, well, what will happen to it, the curve, if you square these points? The large ones will become, no, everything will be a bit less, won't it? Because you're multiplying numbers that are less than 1 by themselves.
Yeah.
Is that clear as mud? Whoa.
I think so, yeah.
I'm just saying, if that's cos, the square of cos would look a bit more like that. If this is cos,
yeah.
From what angle to what angle?
From 0 to 180.
Good, yes. And then, because all of these y values are 1 or less, we'd start at 1. The squares of them are going to be, well, they've got to start here and end up there. And we think it would have a similar curvature, but just not as pronounced, I think.
Right, okay.
Let's make sure of that. Because, hide controls. Desmos, did we have that open? No. Cos x, cos squared x. Yeah. Ah, yes, I neglected. The red one is just cos, right?
Mm.
But you can see how the blue one, when I was
Yeah, I see.
considering the curvature underneath there, I said it would go under, but then I neglected that it would have to start curving anti-clockwise again.
Yeah.
So notice they've both got a point. No, the blue one, notice it's got a point of inflection about there, hasn't it?
Yeah.
I was about to say the red one too, but no. The red one's point of inflection is actually on the x-axis.
Mm.
It's only on the x-axis that the red one, cos itself, starts to curve the other way. So the steering wheel is straight ahead at that point, and then you're turning left.
Mm. Okay.
So you've got that, and then plus sine x. We might as well see what it looks like now. If we add that to sine x plus cos squared x, whoa. I think it's giving me a warning sign, is it? Don't know what it means by that. Why should sine x plus cos x be cause for a warning? Yeah, it's because I've got power of 0, is it, up there? No, not cos of 2x. Cos squared of.
Oh no, you got
Finally. Yeah. See the green one?
yeah.
So that's what we're talking about. You know,
Right.
no mean feat to sketch that, and they're not expecting us to.
Okay.
But they want us to find the stationary points, which this graph has automatically signaled here and here and here and here, hasn't it?
And at the bottom.
And at the bottom, sorry. Yes, quite. So let's set about finding those, just using algebra.
So you're going to differentiate.
Yeah.
Y equals cos squared plus sine x.
Yeah.
Cos squared x plus sine x.
So how shall we pass cos squared x plus sine x? Well, the plus is inviting us to do this separately from that.
Mm.
So let's deal with cos squared x first of all. How does that pass? How would you differentiate it? I would be hoping that you think of it like that.
Yeah, and then squared outside.
Exactly. So that dy dx becomes
2 cos x.
Yeah.
Times minus sine x.
Exactly. Good. Splendid. Which we could simplify maybe.
Minus 2 cos x sine x.
Yes. And actually, 2 sine x cos x might remind us of what form?
Sure.
It's the expansion of which double angle?
Sine to sine to a sine to x.
Yeah. So we've actually got minus sine 2x there.
Yeah.
But I'm going to undo that so that we can carry on and put plus sine x, which of course differentiates to
Cos x.
Yeah. which we could now simplify. And we said that would be minus 2. Well, I might as well put the positive one first. Cos x, in which case I don't think the double angle was such a great idea, because we might as well say cos x outside and what inside?
3.
Nope. How many cos x have we got here?
1.
If it's not a silly question. 1. Good. How many cos x have we got here?
Oh yeah, that's one thing. Okay. Minus 2 sine x.
Minus 2 sine x is how many cos x, isn't it? Yeah. So it's this that we want to set to
2 set equal to 0.
Yeah. Which we might, you know, whereas if we'd had a double angle here, if we thought of that as sine 2x, then solving the equation isn't going to be as easy. So this is better. So solve this equation.
So now you can say cos x equals 0 or
exactly
1 minus 2 sine x equals 0.
In which case sine x equals?
In which case sine x equals minus 0.5.
Minus?
.5.
Just a half, yeah? If cos x is 0, the angle must be?
The angle must be.
So we're what time on the clock?
We are.
Oh, sorry. Did you say 10?
Huh? 10? No.
No, good. What time on the clock is 0 angle?
The time on the clock is 3.
Yeah. And cos on the clock is, if it's a unit circle, cos is the which coordinate of the point on the circle, which is at 3 o'clock. How do we think of cos on the unit circle?
Cos is adjacent over hypotenuse.
Right, but if the hypotenuse is 1, cos is just adjacent.
Yeah, so it's
and
0.
remember that on the unit circle, the trick is to see that cos just means the
adjacent.
Yeah, but if we're on the unit circle,
oh, the height.
That would be the sine, because that would be the opposite. Height would be the sine value of any point. So the y value would be the sine of any point. It's the x coordinate, yes. So if we're at 3 o'clock, we think, oh, so cos is just the x coordinate. Simple as that. See, this is how simple the unit circle can be. If you know, if you're in an angle, in a position where it's easy to think of the hypotenuse as being 1. The hypotenuse is the clock hand, and that's 1. Well, the adjacent side is just going to be the x coordinate of that. And this is an xy grid, remember?
So 1.
So 1. Oh, right. Scratch that. I'm asking the wrong question, aren't I? Jesus, sorry. What did I say? An angle of 1. Where are we on the clock? I did say where are we on the clock, but the cosine is 0. Sorry, my bad. Terrible. Where are we on the clock? Not at 3 o'clock. No, we both made the same mistake there, and I probably deflected you into it. In which case, sorry. The question is, where are we on the clock, but not 3 o'clock? Because we're asking where the x coordinate, the cos value, is 0.
It's 90, isn't it?
So it's 90 or
Or 180?
no, the x value there is,
Oh, no, I'm being stupid. 270 even.
yeah. But I say the x value, it is important not to confuse this x with this x. That's true. Perhaps it would be better to use theta here. Perhaps that's why I got confused. Who knows? But no excuse. And x equals either 90, but in radians they want it,
Pi over 2. Or
or
3 pi over 2.
3 pi over 2. Good. Or if it's sine x is a half. Now, what points on the circle? Remember, sine is interpreted how for the point on the circle?
Sine is interpreted by opposite over hypotenuse.
But if the hypotenuse is 1, it's just opposite.
Yeah, so it's just the height.
What are my problems today? Sine vertical, cos horizontal, right? So which points on the circle have a y value of a half?
Which point on the circle? Y value of a half.
Radius is 1, remember.
Uh, 45 degrees.
I mean, that's a reasonable guess. It doesn't quite work, because if that was 1, this would be 1, and then the hypotenuse would be,
I thought the y value was a half.
true. If that's a half and that's a half, then the hypotenuse would be, thing is, we do tend to use, it's with 45 degrees that we tend to depart from insisting that the hypotenuse is 1. So we do tend to do this. Okay. That's my excuse. But yeah, we're hoping that that's a half when this is 1, but that won't work, will it? You won't get 1 here. What will you get?
You'll get if you get a root of a half.
Exactly. Yeah. Which is not what we want. Because yeah, a quarter plus a quarter is a half. Yeah, root of a half. So the question is, it's not 45. Because by the way, what is the sine of 45? Let's work that out. So if the opposite is equal to the adjacent, because the angle is 45, the tangent is 1. Do Pythagoras on that to solve for x, and what have you got?
Okay. Root 1 will equal root x plus root x.
You mean x squared plus x squared? No. What do you mean?
Wait, x squared plus, yeah, so 2x squared will equal 1.
Good. So x squared equals?
So x squared equals 0.5.
And x would equal?
Root 0.5.
Or root of a half, I would rather say.
Yeah.
And that's what we tend to call it. 1 over root 2 is how I remember it, but it's a matter of taste. You could say root 0.5. I wouldn't, but you could. So no, it's not 45 degrees or pi over 4, which has a sine of a half.
Mm.
The sine of 45 is 1 over root 2. Where else might it be on the unit circle that has a y value of a half? I mean, you went halfway from here up to here. Now that's forgivable because here the sine is 1 and here the sine is 0. But notice it's not a linear function. It's not a straight line. If it had been a straight line, then 45 degrees would have been it. That would have a y value of a half then.
Right, okay.
Do you think the y value of a half, you see, the reason it's not 45 is your y value is up here for
Oh, yeah.
the y, because that's 1 over root 2.
Yeah.
It's rather higher
Okay.
than a half. There's a half, there's 1 over root 2. But on the circle, our y value is a half. You see, we're further down than 45, aren't we?
It's 30 degrees.
Maybe. Seems a reasonable guess, doesn't it? 30 is a common one. Well, yeah, because between 2 o'clock there and 4 o'clock there, that makes what kind of triangle?
An equilateral.
Yeah. In which the angles are all
The same.
and therefore
are 60 degrees.
in which case this angle must be
30 degrees.
so it works out.
Yeah.
The y value here is a half if that's 1 because it's got to be a half of whatever the hypotenuse is, the radius.
Yeah.
So
okay.
Really make the unit circle your friend, and then you see that if sine x is a half, then we're either here on the circle, in which case x equals x being the angle here. Yeah, it would be neater if they'd used theta. But then the angle is what when sine is a half? We've said the angle is probably
30 degrees.
Or in radians?
Or in radians, that would be pi over 6.
Good. Or can you see where else on the circle would fit the same bill?
5 pi over 6.
Well done. Over here. Cool.
Good.
Find the coordinates of the stationary points. Well, apparently we've got 4 x values. So taking them each in turn and getting practice with the unit circle, because they want to give us 6 marks for this. So it's probably partly just an exercise in using a unit circle. So let's collect these pairs of coordinates. We've got an x value of pi over 2 and a y value of what then?
X value of pi over 2 and a y value of
So taking them each in turn, what's cos of pi over 2?
Cos of pi over 2.
Use the unit circle. Cos is the x coordinate. What time are we on the clock if it's pi over 2?
12.
12 o'clock. What's the cos value then?
0.
0. So cos squared x will be
0.
and sine will be the y value at the same time on the clock, which is
what?
So 1.
1, yeah.
So 1 there. Next one, 3 pi over 2. 270 degrees. Down at 6 o'clock. Cos is
0.
again. So cos squared is 0 again. And sine this time is
1. -1.
-1, isn't it? Because we're down at 6 o'clock.
Yeah.
Good. Pi over 6. What's cos of pi over 6? What time are we on the clock?
30 degrees.
Yes.
So we're at 2.
2 o'clock. Good. Now, what's cos at that time?
Cos is
So you do need to do Pythagoras, but it's one that you'll do again and again and get used and more or less learn by heart.
so you 0.5. Okay, so root 3/4.
Which we simplified to a little bit.
Not sure. Root of 3/4.
Root of 3/4, but the denominator is 4, so root 4 is.
Say that again.
Well, because we've got root 3 over 4, that's like root 3 over root 4, isn't it?
Okay, so root 3 over 2.
Yeah.
Okay.
So cos squared is going to be what?
So cos squared is going to be root 3 over 2 squared.
Yes, which is?
Which is 3 over 4.
Of course, that's how we got here, isn't it? We square rooted 3/4.
Mm.
But cos squared is just going to be 3/4. After all, it's the square on that side of the triangle, which is going to be 1 minus 1/4.
Yeah.
So we've got 3/4 plus sine of 30 degrees is.
Sine of 30 degrees is half.
Yes. So y is.
So y is 0.5, half.
Oh, sorry, the y value at that point on the unit circle, true. But so the output of the whole function y here is.
What we're saying, a half plus.
Cos squared was
3/4.
Yep. So in total.
5/4.
Good. And finally, for 5 pi over 6, what's cos if you're here at 10 o'clock? Cos is just the x coordinate of that.
Yeah, cos is. Oh, my battery's running low.
Oh, do you want to get back to me? So remember, the horizontal axis in the unit circle is cos. So what's cos of 5 pi over 6?
Cos of pi over 6.
Which is what time on the clock?
Which is 10 o'clock.
10 o'clock. So what's the cos coordinate of that point, 10 o'clock?
It's.
God, all these years, I really ought to have been saying that.
What?
What's the cos coordinate of that time on the clock? Oh, God.
Isn't it? So wouldn't it be like minus 5 over 4? Oh, no. No.
What was the cos coordinate of 2 o'clock?
It's minus root 3 over 4.
Yes. So cos squared of 10 o'clock is going to be
cos squared of is
5
just
pi over 6,
minus 3/4.
which is minus 3/4. Yeah, yeah. And sine at 10 o'clock is
Sine at 10 o'clock is a half.
yes. So altogether,
A half plus 5/4. Isn't it just 5/4? Oh yeah, you were
no.
the first one.
What is it this time? What did you say? Cos?
Oh, minus 3/4.
Oh, sorry, it is 5/4 again. Oh, sorry, yeah. Because it's cos squared. We never did the squaring, perhaps, or did we? I don't know. So yeah, the square of, even though cos of 10 o'clock is the negative of cos of 2 o'clock, we're squaring it. And then the sine is also positive. So it's all the same again. It's 5/4. Are you with me there? Because it'd be my fault.
Yeah, I think I am, because it makes it positive because you're squaring it.
Yeah. So, yeah, good. I don't think we missed anything there, but it seems a bit generous, 6 marks for, but it's just unit circle practice, yeah.
Yeah.
I don't think they would reward you that much. But anyway, the maximum point. And of course, what do they mean by the maximum point? That's just another word for what?
I don't know, the highest point on the graph, the highest pi
Yes.
value,
In other words, it's one kind of
stationary point.
or turning point. Exactly. Yeah. So a stationary point, which also happens to be a maximum rather than a minimum, because of course all turning points are either a local maximum or a local minimum. Not a global maximum, or they might ask you sometimes for the global maximum or minimum, if there is one, which there might not be, because it might not have a maximum. It might go on to infinity. Right. The maximum point on the curve with this equation, whatever it looks like, and let's not even worry too much. Let's just think, whatever it looks like, we know how to find the maximum point, don't we?
Yep.
So y equals x times root sine x. Shall we write that as sine x
and a half
to the half? Good. Then what we've got is a product of x and this composite. Differentiate.
Yeah, okay. So you'd get 1.
Good. Times that. Now,
sine x.
no, we probably don't need it. We probably could use a common denominator, funnily enough, even though it's not a fraction. Just in case, let's say, okay, let's call that sine x over root sine x, because it is, isn't it? Because sine x is root sine x times root sine x, isn't it? So if that's over root sine x, they cancel and you're left with root sine x.
Wouldn't it just be sine x over sine x? Oh no.
You see, sine x is root sine times root sine, and one of them is cancelling with that one on the bottom.
Okay, right.
And it's only because I've done it before, that I can see what's ahead. But it is going to be used just as it often is with a fraction. This is what the quotient rule does, really, provides a common denominator. Anyway, carry on telling me what to do. Next.
And then Then you get plus
Good.
x times a half
Yeah.
sine x half sine x to the minus 0.5
Yeah.
times
Good.
cos x.
Exactly. Exactly. So let's simplify.
Then you get sine x over root sine x.
Yeah.
Plus I'm not quite sure how to say it now you've done it in that form.
I mean, we'll just think about what sine x to the power of a half, to the power of minus a half, rewrites as.
Sine x over minus root sine x.
Sorry, say again. How can you rewrite sine x to the power of minus a half?
Would it be sine x over minus root sine x?
Well, yeah, that would be the complicated version. No, it wouldn't. Sorry, it wouldn't be sine x over that. No. What's another way of writing x to the minus a half?
Another way of writing x to the minus a half would be minus x minus root x, or 1 over x. No, it's 1. It would be 1 over x to the half, wouldn't it?
That's better. Yes, exactly. Or 1 over root x if we prefer.
Mm.
So what about this?
So it'd be 1 over root sine x.
Now do you see where this came from?
So yeah, it would just be plus plus a half
Yeah, good.
x
Yeah,
times cos plus half x cos x. Yeah.
quite. Yes, job done.
Okay.
So there's our gradient function. What did they want?
Set it equal to 0. Find the highest point.
Yeah. So they want to find the maximum point, which is a kind of turning point, which you. Oh no, hang on. Yes. Okay. Yeah. Hmm. Okay. So a maximum point is a turning point of one kind or another. And how do we distinguish between the two kinds of turning point? Between a maximum and a minimum? How do we identify whether a turning point is a max or a min?
Because we know that, well, we can work them out, and then whichever one's bigger.
Oh God, yes, you could do that. But then remember, it's not a global maximum. If we knew that there was only one kind of each, that would do the trick. But if one is bigger than another, I mean, yeah, if we know that we found all of them, we could do that. But it's quicker and neater. And it's funny that we didn't mention this yesterday, because how do we find an inflection point?
By differentiating twice and then solving for 0.
And solving for 0, because an inflection point is where the curvature is changing from one kind to another.
Yeah.
But to distinguish between a maximum and a minimum point, it's not like the second derivative is going to be 0, which will be in between those points. But it is like the second derivative is going to be what kind of thing for a maximum and what kind of thing for a minimum. What happens for maximum and minimum at the second derivative?
Second derivative. Oh, what happens to them?
Well, that's badly put. I mean, how do we use the second derivative to distinguish between maximum and minimum?
Well, well, the local maximum is gonna be between they'll be between the points.
Between inflection points, true. Okay, so this local maximum is between this inflection point and that inflection point, but we can be more direct.
So the local maximum come after the.
Yeah, but again, that's too much work. It's good work, it's worth investigating, but it's easier than that because remember, why is the inflection point giving us a second derivative of 0? It's because the second derivative is changing from where it was negative to where it's positive. Or here it's changing from where the second derivative is positive because look, we're pointing soon up. That's my mnemonic. That's how I think of the second derivative talking. It's saying if it's positive, then we're headed soon up. It's like eventually up. But of course, if it kept on curving, it would go back round, which would be silly. So it's only a mnemonic. But you've got to somehow or other find your own way of associating a positive second derivative with a minimum rather than a maximum. And a negative second derivative means you're at a maximum rather than a minimum if your first derivative is 0.
Say that bit one more time.
Yeah, that's a bit quick on it. Well, I mean, what we're going to do, what we've done so far is found this. If we set this to 0, then we know we're either here or here.
Yeah.
But then what we also need to decide is whether our curvature is clockwise, in which case the second derivative is what? If the curvature is clockwise, the second derivative must be
positive.
You might think so, because why else might you think so?
Oh no, clockwise. Okay,
but
I
notice
thought
we're curving. Sorry,
misunderstood. Yeah, okay, it would be positive.
We're curving soon down.
Yeah, I thought you meant like would the next point of inflection be going to positive or negative, but it would be
yes, and that would be true. I see your point. Yeah,
but that would be
at
negative.
this point here, if we evaluate it for the x value of this turning point, we'll get a second derivative which is
negative.
Yes. So I think what we'll do is find all the solutions which are x values which make the numerator 0 here, because that'll make the whole first derivative 0. So we'll get a general expression for the x coordinate of a turning point. And then we'll just choose the one where the second derivative would be negative or positive.
Negative?
Yes, because we want the curvature to be clockwise, heading soon down.
Yeah.
So we'll do that. What was I going to say? Can't remember. Anyway, can't have been important. Right. So yeah, let's set this to 0 in order to find the turning points. What should we say next? If this fraction is 0, then what?
Then sine x plus half x cos x equals 0.
Yeah. From there?
You could say half cos x equals minus sine
Half
x.
cos x.
Half x cos x.
I mean, you could say half cos x, sorry, but you could also say half x cos x.
Equals minus sine x.
Good.
I don't know.
Sorry?
Divide. I don't know really.
Yeah, nor do I. I don't quite know where we're going with this. You could divide both sides by cos.
Oh yeah.
Actually, they mentioned tan, didn't they? So this is probably the best thing.
Mm.
So, yeah.
So sine x over cos x.
Or tan x, yeah.
It's tan x, yeah.
But we're not ready to compare with what they say, although it looks pretty similar. In fact, yes, we could keep zero. We could keep it equal to 0, couldn't we?
Mm.
But what we're not sure of yet actually, we don't need to do the second derivative, do we? That's weird. It would be a waste of time because we've already got what we need. That's what they're saying, isn't it?
Yeah.
And we've shown that that follows from us being at any turning point. We've shown that that's true at any turning point, a maximum or a minimum.
Yeah.
So calling it a maximum rather than a turning point is a red herring. I mean, that's already true for any turning point. It might have been nice to find the second derivative to check that it will, in fact, or at least sometimes be a maximum.
Mm.
But just having found that it is sometimes a maximum, that just means that this is still true. So yeah, complete red herring. So we're done there, really.
Yeah.
So a quotient, notice how it always turns out to be a product rule with a chain rule embedded in it.
Mm.
And so do some other concoctions like this one here, even though it's not a quotient. What do I mean by quotient?
A quotient is know this. A quotient.
Quotient is just a fancy word for, or old-fashioned word for. Remember, what do you use? What kind of expression is it that you would differentiate using the quotient rule?
For
differentiation.
What kind of differentiation? Maybe like
You use the quotient rule if you're differentiating a
fraction.
Fraction. Because quotient just means
Fraction.
It does, yeah. Just an old-fashioned word for fraction. Sometimes we, the old-fashioned ones keep going, don't they? Right. So,
what is the quotient rule exactly?
What is the quotient rule?
Yeah.
Yeah. When did we last try differentiating a fraction? Next time. Here was the last time we differentiated a fraction, wasn't it? Here was our fraction.
Mm.
And here was the derivative. Now we differentiated it as a product.
Mm.
Because wherever you've got a fraction, you could think of it as the numerator times 1 over the denominator. So a minus in the power there. So this is what's going on. You've got the chain rule embedded in a product rule. But the quotient rule is doing exactly that. If you call that u over v, then what you've got here is u, and this is 1 over v. And the quotient rule says that the derivative of u over v is u dashed v
Plus
except
dash.
Over, because that's, don't forget, this would be v over v squared. Yeah. But of course I avoided the quotient rule here because it would have given us a power 4 there.
Yeah.
Because it would tell you to square that. So it's u dash times v over v squared plus u times v dashed over v squared. So this is the quotient rule.
Right, okay.
You say u on top, v underneath, and you just put it in that formula.
Yeah.
Which is fine. Then you'd have more simplifying to do. So it's best to do it as a product rule, but not always. Sometimes the quotient rule is even better. Right. But it's just rather interesting that the common denominator was needed here for the same reason as in the quotient rule. The quotient rule is a bit of a blunderbuss in that to get the common denominator, it just says, okay, square v, which is unnecessarily sledgehammer to crack a nut a bit. I'm exaggerating. Right. Next. Actually, I'm going to get out of the habit of, I'll just do this. Canvas size, height. What the hell? Resize. Fine, we've got some more room. Okay. And this one here, number 8. Okay, so if f of x is that function, find f dashed of x. Okay.
Okay.
F of x equals
e to the 0.5x.
Yeah. How shall we pass it? Shall we think about?
Okay. Yeah. Minus.
Oh no, I wasn't worried about decimal versus fraction, but yeah, minus x squared.
Minus x squared.
So f dashed of x will equal what?
F dash of x will equal it will equal half x e.
I was glad when you said a half, and I didn't want to say, oh yeah, let's bother to draw blob, but let's bother to draw blob after all. Times e to the blob. Then I'm not getting why you said half x e to the blob, because the derivative of blob is just
Blob.
What's the derivative of blob? in this case?
Uh,
Oh, the lower version of blob is blob. The
half,
derivative of blob down here is
a half.
just a half, not a half x.
Mm.
So we didn't need that x there. That's all I'm complaining about.
Okay, right.
So I want to lose that. Minus?
Minus,
Oh, and indeed, we can lose the half as well, can't we? Because, or we could lose this half, depending. Let's lose that one on this occasion. Minus.
minus 2x.
Yeah, because that's simple. So let's just simplify it as a half e to the half x minus 2x. Yeah.
Yep.
By evaluating f dashed of 6 and f dashed of 7, show that the curve with equation y equals f of x has a stationary point at x equals p, where p is somewhere between 6 and 7. What they're doing here is inviting you to do, remember when you were considering ways of deciding whether it was a maximum rather than a minimum, you were saying compare with points that are coming earlier and later.
Yeah.
And that's what that's the kind of reasoning they're requiring here.
Yeah, one you'll get a positive and one you'll get a negative.
Positive and negative what?
Gradient.
Gradient, exactly, yes.
6 and 7.
Yeah, perfect, good. So let's do what they asked and say f dashed of 6 is?
Half e to the half to the 3.
E to the cubed, yeah.
Minus 12.
Yes. Now, what is e cubed? We don't know whether it's more or less than 12. So we need to ask a calculator, I guess. Unless we know roughly what e is. Do you? What is it? 2.7 is?
2.7, I think.
Yeah. Yeah. Anyway, if we cube it, and halve it, we get a bit less than 12. We get roughly 10.04. Which is going to be less than 12, and therefore this comes out negative.
Minus
F dashed of 7. And this time it would be 7 or 3.5. Oh no, I never halved the e, did I? Yes, I did. So e to the power of 7 halves over 2, which is 16.56 minus 14, which is greater than 0. And then you would just you probably need to use words to show that you understand. What are some good words to use? Or a diagram. I mean, you could say the gradient function. You could say if that's x and this is f dashed of x, so we're looking at the gradient function itself, then apparently between 6 and 7, what's happening with the graph?
it's there's a stationary point. It's
Oh, well, careful. I'm not talking about f now. I'm talking about f dash.
oh um well, that would be a different line.
Yes, the gradient function is its own line. But what we're interested in is where the gradient function itself, in its own right,
Is so between 6 and 7. Oh, it will touch the x-axis.
yeah, exactly. And it looks
Positive.
like it's coming from underneath there, like that. So you could draw that diagram to explain, or you might prefer to use f itself and just say, look, I know, what was the question? Was it that, oh yes, we don't know whether it's a maximum or a minimum. So it'd be easier to use this explanation, although we do now know that it is a what? Is it a maximum or a minimum?
Which
The f function between 6 and 7. Since the gradient's
so
going from negative to positive,
it's a minimum.
it must be a minimum. That's right.
And because it's going through the
Sorry?
x-axis, and because it's going through the x-axis that it's a the way it's going up like that, that means it's negative as well, and a minimum even.
Yes. Oh, well, we haven't found the second derivative.
Yeah.
And we haven't needed to because we have done, remember earlier, you suggested a method for deciding between max and min. And I said, no, that's too much work. But now we are doing that anyway. So we are in a position to say it must be a minimum because we're going from a negative gradient here, where the tangent is sloping down, to a positive gradient there, sloping up. Therefore, we do know it's a minimum where it's stationary in between.
Yeah.
Well, let's find f dash dash of x just for good measure. Please tell me f dash dash of x.
Well,
here's f dash of x.
Can we write that out?
Sorry?
Do you write that out?
Yeah. Work it out. No, I mean.
I meant write. I said write it out. Just don't know.
Sure. Yeah. I mean.
Yeah. Okay, but we'd get a blob of half x.
Yes.
And so you'd get half e to the half x times half.
Yes.
So you'd get a quarter e to the half x.
Yes, you would. Good.
Minus 2.
Good. Yeah. Our only problem is we don't know the precise x value of the minimum point, or do we? No, we never actually solved the first derivative equal to 0.
Oh, yeah.
And that might be a bit hard, which I guess is why they've
gave us numbers.
Chosen that function so that we have to do this kind of reasoning because they wanted us to.
Yeah.
Whereas earlier on I said, don't do that, it's too much like hard work. But they want to know that we can do the hard work if we need to because we can't solve this precisely.
Yeah.
Which is an issue you will be tested on as well. Approximating solutions where it can't be done precisely by saying it's got to be somewhere in between here and here.
Let's see.
Okay. What have we got here? Underestimated again. What did I say now? I wonder if I made a boo-boo. No. Fine. Use calculus to find the coordinates of the turning points of the graph of the function f. What do you suggest?
What does it mean by use calculus?
Oh, what's calculus? Basically.
Numbers?
Calculation is, yes, but calculus is just the historical, for historical reasons, calculus just is the name we give to either differentiation or integration. That's all. It just means either one.
Oh, okay.
One being the reverse of the other. So use calculus means use one or the other.
Okay.
And which one do they mean? Probably
differentiation, probably.
Differentiation, because it's about turning points, gradients.
To find turning points of the graph y equals f of x, show that y equals, so if we differentiate e to the 2x,
yeah,
sine 2x, so we could pass that as e to the 2x times 2. Oh no, actually.
Yes, when you differentiate, you're saying that's going to be e to the 2x times 2. Yeah, sure.
Yeah, and then sine 2x.
Oh, the only trouble is, and then sine 2x. It's not saying plus this separate problem, which we can do
times.
separately.
Yeah, no, it's times sine 2x.
So we've got to acknowledge really that we are dealing with a product rule. It's got a little chain rule inside that bit of it this time. And then there's a little bit of chain rule going on here, isn't there? But the inner function, again, is rather simple. Well, it's simple in both cases. So you wouldn't need to, you certainly wouldn't want to be using a u substitution or anything like that. When you do this, you just think about the inner function while you're deciding the derivatives. So, so it's a product, and we need to treat it as a product rule differentiation. So the derivative will be equal to what?
E to the 2x, well. What did I just say before?
The adjustment you mentioned before. Because of that composite nature, the chain rule says the derivative will be
2e to the 2x.
Yes, good.
And then sine times sine 2x.
Times sine 2x, good.
Plus e to the 2x.
Pure and simple. And
times sine to the 2x. Oh, no. Times cos 2x.
Yeah.
Times 2 cos
2. So it's 2 cos 2x, you see?
Yeah.
So we don't worry too much about the chain rule. We don't do a u substitution, or probably don't bother being careful about the diagram when it's just a constant inside there and we're differentiating. I mean, when you're integrating, it's a different matter. Then the constant, even if the inner derivative is just a constant, the effects are more difficult. But if we're going down, if we're differentiating, then that 2 just goes there. So we could bring 2e to the 2x outside and simplify inside, couldn't we?
Yep. Sine 2x plus a half.
True, if it weren't for this.
Okay, plus cos 2x.
Yeah. Because I took the 2 out as well, you see, because they both have
Yeah.
2.
And then differentiate that.
Yeah. And yet they haven't asked us to differentiate again until part B. So perhaps this, the first derivative, was enough perhaps to
Oh yeah.
find the coordinates if we don't need to know whether they're max or min. If it's indifferent between max and min, then we can go ahead and do what?
We can say 2e to the 2x equals 0.
Yeah.
Or
But this is on the assumption that, I mean, we haven't said yet that, okay, on the assumption that this is equal to 0 because we're at a turning point, that's when, yes, you're right. Either this part of the product must be 0.
Yep.
In which case, what?
In which case,
I mean, we could cancel the 2 because 2 can't be 0, can it?
yeah, no.
We might as well divide both sides by 2.
Yeah. E to the 2x equals 0.
And how could that happen?
If x equals 0, I don't know.
No, if x was 0, what would e to the 2x be?
1.
Yeah. And if x was something very negative, like minus 100, you'd have e to the minus 200. And that would still be positive, if you think about it.
Tiny. Yeah.
The thing with, you've got an exponential function here, and what does the graph look like?
It looks like it tends to the x-axis.
That's right, but never reaches it. And is never 0.
Yes.
So that just can't happen. Sort of inconsistency or syntax error.
Right, okay.
Or
sine 2x plus cos 2x.
Yeah. Is equal to 0, in which case sine 2x equals?
In which case sine 2x equals cos minus cos 2x.
In which case?
In which case sine x equals minus cos x.
True. No, sorry, not true.
True.
You're trying to cancel those 2's, were you?
Yeah.
Yeah, that's understandable, but not legal. Be interesting to I think we'll skirt the issue for now, but no, it's just illegal.
Yeah. Could you say like sine, I don't know. Would you divide them both by cos or something?
Yes. Divide both sides by cos 2x.
Yeah, so then you've got tan 2x.
Tan 2x
equals minus 1.
Yeah. In which case, where are we on the unit circle? Remember, the vertical axis is sine, the horizontal axis is cos. What's tan then?
Tan is the well, the hypotenuse, because over adjacent.
Not sure I agree with that. That's a bit high, by the way. Vertical is sine, horizontal is cos. So tan means y over x, or vertical over horizontal, sine over cos. So
Right.
what points, if you just think of this as an xy grid,
Yeah.
I mean, basically, if sine over cos is -1,
Yeah.
then basically, whatever the top is, call it A, must be the negative of the bottom, call it A. Or, in other words, the two coordinates are just going to be the negative of each other. We're looking at coordinates like x minus x.
Yeah.
What's the
Okay.
equation of the set of all the points which are the negative, whose coordinates are the negative of each other?
Just settled. What's that?
I mean, what line has this as a general point? Where are the x and y coordinates equal to each other?
X equals y.
Where y equals x, yes, which is there, isn't it?
Yeah.
So which line has this as a general point?
Y equals minus x.
Y equals minus x, which is here, isn't it?
Yeah.
Roughly. Try again. In other words, we're either here or here.
Yeah.
But if it's at 45 degrees from the horizontal, that must mean we are either where or where. The angle must be what or what? Oh no, it's all right. The domain is only 0 to pi, but we'll still deal with this because it's 2x, so we'll be halving it soon. But 2x must be either here, and we are dealing in radians, so that's like 10:30 on the clock. What angle is that? Round from 3 o'clock.
That is what? How have you got 2x's there?
What, here?
Yeah. How have you got that point on the unit circle?
Because the tan is -1. So the y coordinate has got to be the opposite sign to the otherwise equal x coordinate. So we've got to be here on this line somewhere.
Right. Okay. Then.
In other words, we've got to be on the line y equals -x because the general point is that the y value is the negative of the x value. The y value is the negative of the x. Yeah.
So that would equal -1 as well.
And remember from cast, is just telling you where the things are positive.
Yeah.
Otherwise, so here and here is where a tan comes out positive. So here and here is where a tan comes out negative.
Yeah. Understand that.
So 2x is either here, which is what angle? Round from 3 o'clock. What's that angle there?
135.
But in radians?
3 pi over 2.
No, that's down here.
Oh, that would be oh God. So that's 1, 2, that's 3/4 pi.
Good. Or this, which is which angle?
Or 6/4 pi.
I agree with 4 if you're saying that's 4 to 9 o'clock. But then you've got another 1, 2, 3/4, haven't you?
So 6/4. 6 pi.
Plus 3/4, don't forget.
Hmm?
4/4. Let's go in quarters of pi. 1/4, 2/4, 3/4, 4/4,
7.
5/4, 7/4 of pi is what you meant.
Yeah. Okay.
Yeah. Great. In which case x equals
X equals 3 pi over 8.
good.
Or 7 pi over 8.
Would be the values of x. Is that what they wanted? For the turning points on the graph. Yes. And they want the y coordinates as well, which I'm sure we could give them. Let's leave it there for now and carry on maybe, or do something else another time. Yep.
Yeah.
Great.
Yep.
See you there.
All right then. Cheers,
Okay.
Tom.
Cheers, Ollie. Bye.
See you later. Bye bye.